Well, hello again. This is Roger Koch Barr, the instructor for bioelectricity. We are in the third week, week 3, and this is lecture 4 of the third week. The subject of this lecture is the passive simulation. Now keep in mind what we are doing here is we are building our engine, figuring out why things happen in bioelectricity. But the passive simulation is a reference point. First, we have to see what happens if the tissue is not alive. Then we'll come back in the next segment and say, now in comparison, what happens if it is alive? But we need this baseline so that we have something to compare against. I'm going to show you a series of slides that look like this one. And so I want to go through this slowly so that you see that these slides are rich in detail and you can look at these whenever you want to and know immediately what they are. Also, I thought I'd explain it this time through, and then in subsequent times that we look at figures that are similar, I just assume you would know what the layout would be. So first of all, up at the top, there's a sketch. The importance of the sketch is to show, if you have a fiber, where the different electrodes are. But here we see that there's the keyword clamp on. And where it says clamp on, that means that the spatial change has been eliminated. That is, where clamp on appears, where this word clamp on appears in the sketch, that says everything, all the different spatial variation that might exist has been eliminated. Now let's look at the stimulus. Notice down here the word stimulus, and over here to the right is the graph of the stimulus. This is a graph of the membrane current as a function of time. Time is in microseconds. And this particular stimulus, the duration of the stimulus right here, that duration, 400 microseconds. Only less than 1/2 of 1 millisecond. There's a vertical bar that's drawn here. See this vertical bar? And that's drawn at time 0. Time 0 is displaced a little bit off the axis so that you have a chance to see that before time 0, there is stimulus is 0. And then, of course, after the stimulus is over, all along here, the value of the stimulus is 0. When it says on this graph, I equals 0.1, right there, that means that on the red curve, which in this program is thought of as the curve labeled I, the the red curve is displaced upward by 1/10 of the full scale of the graph. That's just done so that you can see that the baseline of the graph right here is flat and in fact is equal to 0. It's a way of actually looking at the 0 of the plotted information. This scale I equals 0.1. If you've used an oscilloscope, this is similar to the knob that moves the trace up and down on the front of the oscilloscope. Now, of course, what's most interesting to us in these simulations is the response. So let's look at the response of the passive tissue. Here we have it. It's in this graph. So voltage in millivolts. And we see that what happens is that during the stimulus, voltage rises. So during this time, during the stimulus, voltage rises. It rises more or less in a straight line as time goes by. If the stimulus continued on and on and on, which it does not, but if it did, this curve would go up and curve over like that. But as we're looking at just the first part of the curve, the response is more or less a line. Now let's think about the response after the stimulus is over. You would say, after the stimulus is over, then the stimulus current, as we see right here, is equal to 0. On the other hand, the voltage up here is not 0. Why doesn't that voltage go back to 0 right away? After all, the stimulus is all over. So why doesn't the response go back to 0 right away? Well, you could say, I think I have the explanation. What's happening is that within the membrane, we have a resistive path and a capacitive path. During the stimulus, while the stimulus was underway, we were putting charges on this capacitor, and as we did so, the voltage was rising. Of course, some charges were flowing through the resistor, but a lot of charges were going to the capacitor. Now, once the stimulus is over, these charges that have been accumulated flow back around through the resistor and out, or in this case over to the minuses. The pluses go to the minuses, or the minuses to the pluses, all depending on what kinds of ions are present, so that the membrane capacitance is discharging through the membrane resistance. And that capacitive discharge is what we are seeing during this whole entire decline that's taking place after the stimulus is finished. It's a process that declines exponentially, as you'd expect. So the short stimulus pulse has, relatively speaking, a long response. Now, on the other hand, the peak of the stimulus was here, was its highest level. And that was at about 400 microseconds. It's declined quite substantially by 2,500 microseconds, 2 milliseconds. So there is a delayed response. But, it's going away. It'll just a little bit longer, and it'll be pretty much invisible, whatever is left of it. So now let's just talk that through very quickly once again. There's a stimulus for 400 microseconds. As a result, the voltage goes up. When the stimulus goes back to 0, the voltage declines. The decline in voltage is associated with the membrane capacitance now discharging through the membrane resistance. If I say that same thing in words, the stimulus causes an abrupt rise in transmembrane voltage. Vm continues after the stimulus pulse ends. Stimulus Vm returns relatively slowly to the baseline, and what's happening is that the energy that was stored on the capacitor is being dissipated in the resistance. If we talk about this in words, just somewhat more loosely, you could say you put a pulse in. That changes Vm pretty abruptly at the start of the stimulus. But then Vm decays until all of the charge on the capacitor has moved back through the resistance, and the resistance has used up the pulse's energy. If you think about the relative wave shape, you'd say Vm is a distorted version of the current pulse. It goes up more slowly, and it decays over a longer time. And when you look at all this all together, you'd say, yes, people have known this for a long, long time, having to do with the subject of RC circuits, and it really is not very surprising that you see it in tissue. Oh, I agree. It's not very surprising, but it's nice to have it as a reference point. So here's a beautiful North Carolina meadow. As you think about what happens passively, you can look out into this meadow, which is actually a very active place, although it looks rather calm at the moment. Thank you for watching. We'll see you again in the next segment.